Okay, for our first lesson in Math 285, we will be looking at first order differential equations, and by definition, first order differential equations are equations that relate the rate of change of the dependent variable, which is also referred to as the output variable, with respect to the rate of change of the independent variable. And the independent variable is also referred to as the input variable. And a sample of a first order differential equation, something fairly basic, we have with dy over dx is equal to 4. So you're looking at the change of y with respect to the change of x, and here we have that rate of change set equal to the constant 4. And so we have in this particular equation, y is the dependent variable, x the independent. Another case of what we have with the first order differential equation is what we have in the case of what we have with dz over dt is equal to z plus 4 all over t minus 7. So here you're looking at the rate of change of z with respect to that of t. And so we have in this particular equation, z is the dependent variable again. So like y, in the first equation, z is the dependent variable, and y and z, are respectively referring to the output, whereas in the case of what we have in the second equation, t is the independent variable. So we have x and t to be the input variables, in their respective equations. Now, a feature that we have regarding first order differential equations is that a first order differential equation is going to result in one arbitrary constant. So looking at referencing what we have for these two equations, and looking at highlighting what we're going to be regarding as the arbitrary constant, we can go ahead and be looking at solving for the dependent variable for what we have in these two equations. So again, going back to dy over dx is equal to 4. We're looking at solving for y. So we have, and you have seen this in earlier courses in the calculus sequencing, we have the rate of change of y with respect to x is equal to 4, and we can set things up along the lines of separating the variables. So if we multiply both sides of the equation by dx, so we're going to have dy isolated, and that is equal to 4 dx. And upon completely separating the variables, or in this case the differentials, we can now perform integration on both sides. So looking at what we have here, and I'm going to break this down in terms of what you could regard as being a couple of subconstants, but we're looking at consolidating as a single constant. So for the left-hand side, now the antiderivative of dy is going to be y, and we can say at the moment, let's say we have y plus c sub 1, and for what we have on the right, we have for the antiderivative of 4, we have 4x, and we'll say that we have plus c sub 2. And I'm looking at isolating y. So if I move the c sub 1 over, so we have that y will be by itself. And to the right, so I have y is equal to 4x. And here we have for the difference of constants, we have c sub 2 minus c sub 1. And we're going to have here that the difference of constants will be a constant. And we can just call this most any letter. We'll just say the letter c. So we have for that solution, we have that y is equal to 4x plus c and again we're going to have with the letter c, that is going to be the arbitrary constant. and looking at what we're going to have in the case of the next equation where we have involved, okay, the variables z and t. Okay, so we have dz over dt is equal to z plus 4 all over t minus 3. Okay, so if we look at separating the variables, okay, what we have in z apart from that which we have in t, okay, so we can simultaneously divide by z plus 4 and multiply by the differential dt. Okay, so we have in the rewrite, okay, we have dz all over z plus 4 is equal to dt all over t minus 3. And with the complete separation of variables, we can go ahead and integrate. All right, and looking at what we have for the expressions. Okay, so we have first order binomials in the letters z and t. Okay, and for z plus 4, now the derivative with respect to dz, okay, or with respect to the variable z, that will go to 1, and with respect to t, the derivative of t minus 3 goes to 1. So no special kind of substitution methodology will be necessary. Okay, and for the antiderivative of the reciprocal of a linear expression, okay, this is going to be a natural logarithm. Okay, so here we'll have the natural logarithm of the absolute value of z plus 4, and technically I could add a constant like c sub 1 again, but I think I would just keep the constant this time around solely on the right hand side. Okay, and for what we have to the right, okay, you have the antiderivative of the reciprocal of t minus 3. So this will be the natural logarithm of the absolute value of t minus 3 followed by a constant. Now we're looking at solving for z, and I want to take care of the natural logarithm. Okay, and that which will undo the presence of natural logarithms would be utilizing the natural logarithm exponential base e. Okay, so we have e to the natural logarithm of the absolute value of z plus 4 equals e to the natural logarithm of the absolute value of t minus 3 followed by the addition of c. All right, and so for what we have in this particular case is I'm just going to rewrite this statement. Okay, and for what we have, again, just taking a bit of reverse of what we have with the product property. Okay, I'm just going to take the reverse of the product property, and for here we have e to the natural logarithm of the absolute value of z plus 4 is equal to e to the natural logarithm of the absolute value of t minus 3 times e to the constant. And we can say that for a constant raised to a constant, okay, that will be a constant itself. Constant to a constant is a constant. And we'll say that we have, in this particular case, we'll say that e to the c is equal to a. So for what I'm going to have here, have e to the natural logarithm of the absolute value of z plus 4. So e and ln will take care of each other. So this will go to the absolute value of z plus 4. And we have e to the natural logarithm of the absolute value of t minus 3. This will go to the absolute value of t minus 3. E to the c again we have going to a. And performing the commutative property of multiplication, we say we have a times the absolute value of t minus 3. And getting out of the absolute value notation, okay, like you had the positive and negative of z plus 4, we'll have the absolute value of z plus 4. So I'm just going to take out absolute value bars. And strictly speaking, okay, we have, like for A, like acknowledging the potential existence of both positives and negatives. I say that z plus 4 is equal to plus or minus A times the quantity of t minus 3. And we can say that, just to put it in terms of a single constant term, we'll just say that alpha as a single letter will reference both positive and negative 8. So we're going to have in the rewrite, okay, we have z plus 4 is equal to alpha times the quantity of t minus 3, and isolating z upon taking 4 away from both sides, we have that z is equal to alpha times the quantity of t minus 3 followed by the subtraction of 4. And just like c in the first equation, okay, this time around we have for alpha, okay, that is going to be the arbitrary constant. All right, and looking at solving for first order differential equations, let's see what we get in terms of solving for y for these 3 particular items.